Hello, everyone on YouTube. We are starting Emplan's Paper Club. Today, I'm going to present. My name is Vahan, Research Director at Emplan. I'm going to share my screen and we can get started. Cool. Okay. Can everybody see my screen?
Yeah.
Cool. So I saw this paper on Google Scholar as a recommendation, and I read the title, and then I was like, this doesn't sound right, because the title is on representing linear programs by graph neural networks. So if you think about it, the title is already interesting and maybe kind of pointless, but we see that maybe not so much. The idea is that the authors represent linear optimization problems, LPs, as a GNN and train a GNN to solve LP, which kind of is strange, right? Because LP is the simplest optimization problem you can think of, and GNN is a fairly complicated non-convex optimization problem, at least for the training part.
What's a program, a linear program?
Yes, it's an optimization problem, except your, I show the formulas. It's an optimization problem where the objective function is a linear function and constraints are all linear. Okay.
But I don't think it's weird because it's like the optimization is very compute heavy, and they're trying to replace the optimization with a pass through of a function, like a
Right. So I think it's weird because LPs you can solve up to billion variables. Training on a billion large graph, if not as simple, right? That's why it has a practical.
So you feel like it doesn't have a practical use?
Maybe not so much. I just present quickly here what LPs. Good question, because we don't talk about optimization here as much. LPs were created before World War II to solve logistic problems. They are still very common. Basically,
I think they're used in like supply chain.
Scheduling program. Basically, in a three-dimensional space. Yeah. Right. You will create a three-dimensional constraint area. This is important because we will talk about measures and the size of the constraint space. I want to give you an example here. Let's say it's a cube, right? In this case, doesn't have to be a cube. It can also be.
I think it's always a cube, right?
No, it's always intersection of hyperspace. It can also be more complex, but
it has to be some rectangular
spaces. But it has to be like linear spaces.
But wouldn't the constraint have a lower dimension than the actual problem? The cube is also three-dimensional with three-dimensional space.
Yeah, and then you would have an objective function. Let's say another line. Let's say up here. In this paper, we only talk about minimization, but you can always convert. Let's assume it's always minimization. You would have some function here, right? Let's say hyperplane. Then you want to find this hyperplane that's minimized, but lays inside this constraint space, which can be a cube or any other area constrained by hyperplanes. So each hyperplane is one-dimensional obvious. Okay, so that's an LP. Okay. Obviously, when training a GNN, we are minimizing a much more complicated optimization problem. That's why it got my attention. I was like, why would you do that, right? So before we continue, I want to pose a couple of questions that we want to look for our answers in the paper. The obvious one is, can we extend this theory for mixed integer problems? Mixed integer means you also have constraints saying that your variables are integers. Those are the really hard problems. So those kind of problems up to 10,000 variables are very, very difficult to solve unless you have very nice symmetric constraints, right? So that would be an case that applying a GNN would make a difference if you can actually formulate the theory properly. The other question is, so there is a one step here. They transform a linear optimization problem, linear program, LP, into a bipartite graph. And then they study the properties of this graph. Because bipartite graphs are quite generic, can we use that theory for any other problems, right? Both questions, I don't have answers yet, but maybe we can figure out, right? Okay, any comments from Zoom? Let me check if I missed any messages, new people. No, we are good. Okay, so
I can raise my hand if someone's.
or just interrupt me, right? Yeah, if I missed the message. Okay.
Miss your eloquent presentation. I don't know.
Yes. Okay. So the paper starts with an introduction and a bit of state of the art. And then they say they started studying this problem because it has been used in practice. People have applied this experimentally, as in formulate a GNN to solve an LP. I'll explain what the GNN is in a moment. We covered a few GNNs here before, in case there is anyone new. But there have been good experimental results, so they want to find theory explaining why it works. Okay. So GNN basically means, in very broad terms, neural network that works on graphs. Okay. Normally, when we say GNNs, we mean message passing, as in GCN or GAT, all these architectures that rely on passing messages between nodes in the graph. Here it's similar, but it's not exactly the same sort of GNN we have seen before, because the graph is a bipartite graph. Maybe I should show here what the bipartite graph is, and then we can also see how they formulate a linear program as a bipartite graph. Okay. Okay. So, should we do an example? Should we do their example? Actually, let's look at their example here.
Yeah, that might be.
Yeah. So I don't invent on the fly, right? Let's just do the exact same thing, and then it goes smoothly.
Okay, Vahan, your camera is facing the.
Better.
How about see something closer? Yeah.
Okay. Okay. There's minimization of a linear function. In this example, they put x1 plus x2 plus x3, right? And then they have some linear constraints subject to some constraints. The idea is that you take variables on one side, constraints on the other side, okay? Because bipartite graph means you have nodes here, you have nodes here. Between each other, they're not connected, but they are connected across, right? They don't have to be fully connected. Some of them are, okay? So if you put constraints here, constraints, and variables here, it makes sense that constraints shouldn't be connected to each other, variables shouldn't be connected to each other either. But each variable appears in a constraint, right? So there is a link. So if you look at their example, first one says x1 plus 2x2 plus, so this would be x1, x2, x3. So in our case, this doesn't exist. And then you would have constraint 1, constraint 2, right? And then you would say x1, x2, x3 all appear in here. So this would be all connected, right? Actually, now this becomes fully connected because they're all connected, right? In this case. So
there's no restriction on whether the graph is a DAG or is circular.
no, there is no direction. Because what does direction
Yeah,
mean?
but like a tree. So in principle, this sort of graph can have some.
No, you can't have, you can go like this, right? That's a science.
Yeah, but it looks
Except there are no connections between
yeah.
on each side, but you can actually go compare to the same one. But that's fine. So this is how they create the graph that represents the linear program. The important part here is to also create the features, right? Because you need features in your nodes. So features here are represented, but you have features on each side. So on the constraint side, they noted as V, variable side doubling. Maybe we should just look at this example here. So on the variable side, they designed how it's done, how it's represented. I guess you can do it many different ways. There's one way to do it. This is one way to do it. So the first one would be the objective functions coefficients, first element for each variable. And then the second and third would represent the boundaries for each variable. So x1 is only lower bound by -2, you have -2 infinity. Okay? Same x2, x3 is bounded by -3 infinity. Okay? You also have features for constraints, which is more interesting, right? Because here, one of the features is an inequality sign, right? You have inequality or equality, which either one can be, representing your constraint type. And the other one is the right-hand side, right? So one largely. Okay, those are your feature dimensions. Okay. Obviously, we are going to convert these into numerical features because you can't do ML on these signs. Okay. Any comments? Okay, should be fine. There is a lot of notation here, but I'll try to keep it simple and explain. It took me a while to actually go through all the notation. Okay, so that's how we represent LP as a bipartite graph with features, right? The H on each side is the featured vector. Eventually, before we train a model, we will convert both feature vectors to numeric features of the same dimension. We will bring them to the same dimension. Because otherwise, some of your nodes will have different dimension of features. Won't work. Okay. What?
Why would they have different dimensional features?
Because here you have 1 and inequality. Here you have 1 -2 infinity.
Yeah.
You have to convert them to same dimension, right? Which they do later when training the models. Okay.
Yes, they have a different embedding function for.
Yeah, you have to define an embedding function for each. Yeah. But embedding that maps to the same dimension for both sides. Okay.
To what extent do you feel like this graph is arbitrary, like in design?
Sort of, but there is a nuance in the proofs, right? We have to make sure that assumptions are held, which I think are quite generic. We look at the assumptions in the proofs, because if you don't do it right, you may not be able to find the finite measure, which I think is the problem with mixed integer problems, but we'll get there.
What does it mean ambiguous? Because the graph is pretty much given right to the constraint.
Features.
Like using the features, using the basically that the constraint matrix, like as an adjacency matrix, especially that one, or like the coefficients of the constraint matrix being used as the weights of the edges, especially. I'm like, where's that come from? Like if I were doing this, even though I have like no background in this, I would probably try to incorporate the constraint weight, the constraint weights as features in nodes as opposed to features in like edge weights. Because you don't really use, I don't think we have an intelligent way yet of incorporating edge weights into our models, except for just assuming that they have some like semantic significance to the problem.
Wait, do these edges have weights?
Yeah,
And those are from where?
there. So see where it says the first two equations.
Yeah.
It says so that's like the adjacency. It's like there's that's the like the constraint part of the linear program. There's like basically there's like an AX equals B.
Yeah.
Oh wait, what are the weights on the edges? I didn't realize there were weights on the edges.
So these are the constraints.
Yeah. So if you look in the definition of a linear program, where is it?
They represent
Like AX times B is like a set of constraints where the circle can be less than or equal to, or greater than or equal to. And then the edges are the values of A, the matrix A. The edge weights are the values of A.
Right, this could be also like incorporated into the V1 and V2, right?
Yeah, that's what I was thinking. It's like,
oh yes, of course, yes, because you need to add the matrix here. Yeah, of course, yeah. But that makes sense because if you have 6 elements in your matrix, you actually have 6 edges. So naturally, you put the weights there.
If all the constraints are dense, like that, it doesn't have to be.
What do you mean dense?
That like each constraint touches all the other variables.
Then you would have 0.
Okay, yeah, but 0 weight would be then no.
Then there is no edge. Yeah, there is no edge. That's what I said, right? It doesn't have to be complete.
Yeah.
Graph. If for example x3 is not in the second constraint, you wouldn't have this bottom one, right? The edge would just not be there.
so yeah, that's what my question around arbitrary was, that like whether is there another way you could define a graph for a linear program than this one, or is this like?
I think they took it from other papers. They cite a couple other papers which did experiments, no theory, a lot of experiments. So the main idea here is to actually that's good way to continue, I guess, is to study the expressive power of this model in terms of distinguishing between isometric graphs. So I think that's the cool part of the paper. So let's actually continue, because they do this this WL isomorphism test, and then that's actually a good theory. But before we get there, we need to build some concepts. Yeah.
It says the output is a real number. What's that real number supposed to represent?
Which output? Where?
It says graph neural network, it says LP, and it says the output is a real
the objective value.
Yeah,
So they define two outputs. One is the objective value. The other one is the solution, right? So let's actually scroll down here and look at those. So these hedges give the next layers. So we are going to actually learn many functions. There you go. Here are the functions. Here, so these are the functions we are going to learn. The f's that convert the inputs into embedding for each feature. The output is the output of the GNN, and the L's are the functions for each layer. And they say they use MLP for each of those. Okay, so there is no actual GNN model here, except there are many MLPs working together on a graph.
The MLP would be as big as the number of nodes you have.
What do you mean number?
No, they still do message passing. So they view that essentially all the nodes as like a batch,
Right.
and it's the embedding size that
Must be proportional to the number of.
like it's the size, the dimensionality of your feature vector.
Yeah.
And then, but they use message passing
Yeah.
to like aggregate features. So it's very similar to a GNN.
You mean in this sum part here, right?
Yeah. Well, in all the different, well, I think they use 2 layers in the experiments. And they do message passing where they take like the representation of the first layer and then they aggregate neighbors and then they do it for the second layer. And then
Also in here, right? So all these aggregations are just message passing here.
because I was thinking that they're not wrong when they say, because at some point they say, I was like, oh, is that doesn't seem right. Where they say,
Yeah.
all right. They say, in practice, all the linear functions in GNNs are usually parameterized with multilinear perceptrons. And I was like, what about the message passing layer? But I think they're saying like the elements between the message passing layers are usually multi-layer perceptrons.
Yeah, those functions, right? Those
Yeah.
images, those are all MLPs.
Yeah.
And then they get aggregated. The output from those functions get aggregated. That's why I guess yes, you can. Yeah, that's why it's GNN. It's a bit different from what I've seen before, but I guess it's fine.
The only difference is I guess a lot of GNNs now use attention.
Yeah. There was no need to make it too fancy, I guess, because they don't study generalization. Experiments are all about training. There's another limitation. But they say we develop the theory.
I didn't understand that.
But they develop a theory. Basically, their theory is about the approximation theorem and the universal approximation theorem, right?
But
Yeah.
it seems trivial to me because like to train if you only care about the training set, to generate the labels for the training set, you have to have solved the linear problem.
Yeah.
So you've already solved it and you're training a model to resolve it. But like, why do you care? Like, it's so true because you've already got the solution to the problem that you're training the model on.
Yes, so the idea is that exactly in terms of practical applications, you want to use this trained model on a new linear program, right? So there has been work. They cite one work, I think, that uses GNN to solve a new linear program, but they cite a few others that use it as a starting point for the LP solver. To have a good starting point. Now, this paper is like, okay, sure, you can do that, but we are concerned with the theory to show that this model is a very powerful representation for graphs created by LPs. Basically, it's one thing that GNNs seem to struggle a lot, that they can't distinguish between some isomorphic graphs. And they show that in this case, it's actually not a problem.
I feel like this is a trivial result from a practical standpoint.
From practical, yeah. As I said, right? When even from title, you're like, in practice, this doesn't seem right.
Well, I'm thinking like, it doesn't matter from a theoretical point of view that this is true. If, first of all, we have empirical results suggesting that it can be used for generalization, and this says nothing about generalization.
Yeah.
So
it's so this, you can see this as similar to the universal approximation theorem, right? That you can find a function that can map you can find a new MLP that can approximate any function, right? Similar result here. So if you write that paper with that theorem, it's not about generalization either. I think that's the angle they're taking here.
Okay, fair enough.
Okay.
I wish I could ask the author that question.
Yeah, me too.
Like what are the practical
so this was in archive. So there is a chance.
Didn't get published.
But it was put in archive like 2 days ago. No, okay, a week ago. 1 week ago in archive.
Sounds like a nerves. In the sense that it's got a good, interesting theory.
Yeah. Okay. So let me actually. About the. This is actually I wanted to mention this, Peter. About your question about finding the is how arbitrary is the graph for the LP. So they do actually look at the inverse of the objective of the function that finds the objective function, So as in, you give an a solution, and then can you come back to the graph?
No, I thought that what that does is it takes it says like the optimal objective function value is 10, and give me a solution that meets that objective.
Yes. Okay, so yes, you were talking about the graph from, okay, yeah, fine, yeah. Yeah, okay, that's fine, yeah. So yes, so we look at the solution, and then we find the variables that construct the solution to find the optimal solution. Right? But here they use another known result that says the solution that has the minimal L2 norm is unique, because in general, solution is not unique, right? You can have a flat hyperplane. In the bottom, all of those values will be optimal. In fact, if you have two optimal solutions, you have infinitely many. However, if you minimize the L2 norm, that solution is unique. And then they will use that in their theory.
L2 norm between solutions, right?
Yes, the solutions L2 norm.
I guess it's like whichever solution is closest to the origin. What's the optimal solution?
You have to choose one, right?
So I'm confused about how one set up. So we have a you find this GNN. You supposed to know the objective function?
Yeah, it's encoded in the GNN.
And then we try
Or the
to
inputs to the GNN, sorry.
okay. And so what is the thing when we try to find the actual solution to our problem? Is that
it's a vector?
Yeah, it's a vector, but that vector is not the input to the
No.
So where does the vector fit into the whole machinery?
So you actually use this as a label for one of the objectives they train their models on, which is to come up with the optimal solution.
So the objective function is this one on
the
top.
output, the actual output of the neural network is the
optimal solution.
So there are two models here, right? One returns the X values, the other one returns the result after putting the X values in here. That's the objective value.
So you're not trying to backpropagate through this and to get the input, move the input in such a direction to get the right solution, but rather you try to directly forward predict the right solution.
Then they are saying that if you have the value 10, let's say the X1, X2, X3 are not unique, are not necessarily unique. But if you constrain to finding the minimal norm of X1, X2, X3, then it's unique. Okay. So let's scroll down. A few results here. But the main result here is that let's talk about this the WL test. Okay, because that's actually quite important. Before I talk about the result, let me scroll down.
I have a question about dimension permutation invariance.
Oh yeah, that's actually important. Yes.
What does that mean with respect to like linear programs?
Yes, good point. I was going to talk about it. I forgot. Right. So actually, let me scroll up. We don't need to look at the whiteboard. So if you look at this example, there are two types of invariances they discuss here, right? So if you change the order of variables x1, x2, x3, the result will change accordingly, right? So if you put the coefficient 2 in front of x2, x1, the objective value will change accordingly. But if you change the order of constraints, the result does not change, right? So there are two types of symmetries here. Okay, that's what they mean, and that's important because again, okay, keeping that in mind, let's go back and look at the isomorphism test. Okay, here they talk about the separation power, Weisfelder-Lemon test. So they write a sketch here of the test for the bipartite graph case. The idea is that you take your graph and you iteratively color them using a hashing function. Without going into too many details, but you basically color all nodes. And then after coloring, you end up with two columns. And in the end, you can say if those columns, if you run this algorithm on two graphs, and you say if those columns are the same for both graphs, if they are different for the two graphs, then you can be sure that those graphs are different. However, if they are the same, we don't know if the graphs are different or not. That's the fundamental problem with GNN's expressive power. Okay, so this formula down here is basically says that. Okay, so it's not a, and that's also why we don't even know how difficult it is to determine if two graphs are isomorphic. We don't even know if it's NP complete. We can't even, there is no proof about anything about the complexity.
So if two graphs, so I guess you can get a graph for the linear program, or you can get isomorphic graphs, right? So the solutions of those, or like if you solve those isomorphic, you solve for the objective function, and so are the solutions going to be in the same space?
That's the main result here, right? Yes. So here's an example that says these two graphs are clearly different, but if you run the WL test, you will get that they are the same, but they're not. This is a failed example. However, they notice that there is a common pattern here, which is all those non-isomorphic LPs that failed the test actually are either, both of them are either unbounded, infeasible, or have the same solution, right? That's actually nice. I was skeptical until I got to this part, but I think that's a nice result. Basically, that says, well, unbounded means the minimal value is minus infinity, so you can improve the problem infinitely. Infeasible means the constraint set is empty, there is no solution. And otherwise, if neither of those is true, they have the same solution. Even the solution with the minimum norm is the same.
Wait, it's not that, it's if two programs have the same output with respect to the GNN, then, well, two programs are said to be bounded and feasible, and they have the same output for the GNN, even though they're different linear programs. That just means that they have equivalent solutions, right?
Yes.
Because you could have two linear programs that are bounded and unfeasible and infeasible have different solutions, and then but you would get a different solution with the GNN.
But you mean that say for the register of x1, x2, but just really
No. Equivalent in this case is not with respect to permutation. It'd be like you can literally define two linear programs with whose optimal solution is the same, and they have different constraints.
Because like one is like a space in one direction, and the other.
But the point they make is that these linear programs, they wouldn't pass the WL isomorphism test. Like you would say that they're the same graph when they're not, because they're different linear programs. But it doesn't matter because they have the same solution. So, and the graph will give you, the GNN will give you the same solution. So essentially what the result is saying is that the weakness of GNNs is that they can't distinguish certain graphs that aren't isomorphic from each other. But it doesn't matter in this case because you want
You get the same result anyway.
Solution in that case.
Which may be a nice property of certain types of bipartite graphs. There's another further research area I would look into because if bipartite representing an NP as a bipartite graph is not a new idea. It has been studied before, but maybe we can take a bipartite graph and study its relationship with the LP, or in terms of conditions, and then maybe you can apply GNNs more successfully in terms of their in terms of their representative power, expressive power. Yeah.
You can represent a graph as a bipartite graph, where you do the graph, the edges are
Remove
between
edges.
nodes and edges.
Yeah.
So I was wondering, I wonder if you can do that.
The Euler suite.
I don't know, but we.
Can you? You will have to remove edges.
No, we did it recently in the research that we've been doing.
Ah, you mean switching for?
Yeah, but you can do it for include the nodes and edges and create a bipartite graph between nodes and edges.
Yeah.
So the edges become nodes as well as the nodes, and then the edges are just which ones are connected to each other.
I think that this is one way to prove the Euler's here, the number of vertices plus the number of edges equals to this number, or something like that. It's pretty cool.
It's again plus k minus 1 or something.
Yeah, yes.
Oh yeah. Yeah. Anyway, I thought that was an interesting result because maybe that's another thing to look into, right? Representing things as bipartite graphs and then seeing if the outcome, even though your GNN can't distinguish between those two, maybe it's fine, depending on your problem, right? So that's really the main result here.
I feel like if it was true of graphs in general, there would be a paper on it, right? There's just a lot of people.
But this came out just now, so.
No, I know, but like maybe it's just like there's so many people looking into the court, like what math he can prove with this WL test.
Yeah.
In the last couple of years, how could it not have figured out this general result about graphs?
Yeah, this was this was the main research direction for GNNs last year.
Yeah.
Anyway, a few theorems basically claiming that, right? Let me check if I missed anything important here. Yeah, so again, this other theorem says that that given two graphs with their features, the following three things are equivalent, right? So they're both not distinguishable by the WL test. The output from the GNNs are the same. If they are not distinguishable, then the output is the same. If the output is the same, they are not distinguishable. Okay, it's both ways. And if you have a permutation, this FW returns the solution. The result will have the appropriate permutation for variables. So if you change the variable order, you find the objective solution, it will be just a permutation in the vector.
In the output vector.
Yeah. So basically, if you have x1, x2, x3, you solve the problem with their order changed. The solution will be the same, but the order changed. Right?
Yeah.
Makes sense, right?
There's another architecture which is permutation invariant, which is deep sets.
Oh yeah, we looked into this.
I was just like, I wonder why they didn't use deep sets, but I guess they can't define some kind of interesting graph structure at all.
Deep sets is older, and the idea is that you put things in a set, so it becomes permutation invariant. But the order doesn't matter. So you do only operations like sum and mean. So you keep the invariance. Cool. They also prove results about the. So that's the first result, right? The main thing is that this GNN can distinguish between different LPs and their different results meaningfully. But on top of that, they can show that, okay, if the GNN can distinguish between the solutions, it can also approximate, find a good approximation. So these next theorems are about that. Basically saying that you can find, for any epsilon, you can find a close approximation. Okay, for the given f, there exists an approximation. F is the model you train, really. Okay, cool. A couple of numerical results, nothing major. This is a very theoretical paper. Basically, running experiments to show that the theorems are true. That's all. Only validating the theorems, which say, for example, if you have a bigger set, bigger parameters in your GNNs, so the MLPs are large. At some point, the errors get to 0. You can overfit perfectly. These are all training errors. Okay. And they say, okay, no experiments for testing. And in conclusions, future work, mixed integer linear programming. Very obvious thing. And now, okay, I was thinking, why wouldn't mixed integer in LP work? Because that's, if I understand the measure theory correctly, I think the problem is with defining a measure. So somewhere here, I'll show that there is a result that depends on the boundedness of the measure. Here, this one, right? So you need to define a measure on the graph space. So here they define that measure, saying, well, for the linear parts, it's the best measure, simple, right? The best measure means on a line, it's the length. On a two-dimensional space is the area. 3D is the volume, and so on, right? It's normal. So you can actually, it's bounded. You can have a meaningful measure. For the rest, like the constraints, it's bounded space. You have 3 different constraints. Okay, so that's also fine. But I'm thinking, if you have a mixed integer program, can you actually define a bounded measure? Because if you can't, this is the this theorem here relies on the graph on the graph that we define here. So the graph and the weights being measurable in a with a finite measure. So I think this can be a problem with mixed integer programs. Maybe not, because maybe it's still this discrete, but it's still in a limited space, right?
I guess it's about,
yeah.
Sorry.
No, go ahead.
I was just saying, is it because it's really hard to encode the integer constraint? Like, because if you could encode the integer constraint into the constraints elements of the graph, it would be equivalent, right?
Yeah. So then, how do you
usually how one does it? I think it's when relaxed does constraints. There's a trick to sort of essentially make it continuous, but then almost like an additional objective that sort of pushes it towards integer values, and then it works, I think, surprisingly well for approximate.
Yeah,
I've heard that
you can bound the error using something called group bound or something like that.
I think there's some failure cases to it though, when you just relax the problem and essentially find the solutions and then you round.
Yeah.
Or you can't just round, because if you're in a high dimensional space, where do you round?
Well, that's
if you have 1,000-dimensional space, like you can't really round.
you can sort of, I think, prove that the error won't be beyond a certain bound. I think that
So even before GNNs, there were ML approaches to solving MILPs by trying to predict the cuts, right? So usually MILP is solved by what's called branch and bound or cutting planes.
Yeah.
Right. So that's how you would create those relaxations. Right. So you would create an extra constraint that would relax your problem in a way that it becomes linear. And then you solve the LP and then you continue. But finding those extra constraints is not trivial. So people would train an ML model to try to predict those cuts more accurately. So that's what has been done. Even when I was doing my PhD, my colleagues were doing that. So that's not very new, but maybe similar idea can be used with the GNN. Yeah. Okay. I think that's all. We don't have many people on the Zoom. Any more comments here?
No, I thought it was an interesting paper just because we combined two areas.
Those are actually a huge practical importance, right? If you solve the mixed integer minimizations, I mean, there are companies who sell solvers, right? So you can't even get free version.
Yeah, IBM does that. Simplex.
Yeah. Very cool.
Cool. Thanks all. I'll stop recording.